Okay, guys, now we discuss about topographic effect. What is the problem? We already have, this is the boundary, and it is the Earth's surface. The problem was that we always assume that our data are at the boundary here. But in reality, our measurements are done at the surface of the Earth. Two problems we have here. They are not at the surface of the boundary, which we discussed how to continue this data down to the boundary. Problem of downward continuation that we have discussed. And now the masses or the topographic masses under the points also can affect the value of the gravity values at the surface point. But what we need here at the surface of the boundary here down is the effect without these effects. So now we have to model this topographic effect so that we do not have any mass outside the boundary, and then to continue downward the data at the surface, so the data are placed at the boundary, and then we perform integration or Stokes integration. However, when you perform the integration, you will come to one geoid value. So it means that I get the geoid value, and this geoid is called no topography geoid, NT, or co-geoid. What does it mean? We had to remove the effect and continue the data to come to it so that we can solve the boundary value problem. But by removing this effect and doing downward continuity, we have all changed the Earth actually. We have changed the Earth. Then with this geoid that we compute without the topography is not actually the true geoid. It is something like geoid or co-geoid. Co-geoid. Then we have to change it back to the geoid. Therefore, the effect of the topographic masses should be restored to the co-geoid to make the geoid. So I call this indirect effect or topographic effect. So the geoid is co-geoid plus indirect effect. So what was the problem? One more time. The problem is that the data are not at the surface of the boundary. Why this is not? Because the data are collected at the surface of the Earth and at the level above the sea level or the boundary. So we have two problems here. The data are above the sea level, and also there are topographic masses that will affect this data. So we remove the topographic effect, the effect of topographic masses, and then continue the data downward to the boundary. So now we can perform we can perform the integration, or which is in fact this integration is the solution of boundary value problem, which assumes that there is no mass outside the boundary and the data are at the boundary. Now we have created these conditions. So we solve the integral and come to some values which is called geoid, but since we have changed the Earth by removing these effects, actually it's not the real geoid. It is something similar to geoid. We call it co-geoid. So what can we do? Because it's not the true geoid. So we remove the effect of topographic, we restore the effect of topographic masses again to the geoid to make to the co-geoid to make it geoid. That's the whole story for the topographic effect. Then I can simply say that topographic effect, based on this definition, I simply write TE for topographic effect, so I do not have to repeat it. TE has a direct effect and indirect effect. Direct effect is the effect on the data directly on gravity anomaly, and we correct them to come to the geoid. Good. An indirect one is on the computed result. So I can say that topographic effect is also a remove. When you remove this topography data and continue downward the data, you will compute the geoid. Therefore, we have remove, compute, and the effect that we have removed, you should restore, because we have changed the Earth. The topographic masses are physically there. You cannot ignore them simply. We remove them just to be able to solve the boundary value problem. So again, as you see, topographic effect is also removed and restored to the result. But the question is how to model this topographic effect. So the Newton integral for the potential of any point outside the Earth. Let me draw the figure again. And here is the boundary. Let me call this R, the radius of the Earth. And here we have the topographic heights for all points. The Newton integral gives us the potential, the gravitational potential of any point at the distance r. The colatitude theta and lambda will be G is the Newtonian gravitational constant, surface integral over the whole sphere, a unit sphere or the globe, a surface radial integral from R to R plus H. I will write H prime because H prime means the integration points that they are at the surface. And V is here, for example, the point R, theta, and lambda. I want to compute the effect of this topographic masses on this point. And density of topography over L. L is distance between computation and integration point, then r prime to dr and d sigma. That's the Newton integral. Let me write it, the name. Newton's integral for the potential. Now the question is how to solve this problem. If you want to compute the potential, it's simple. You have this formula. You have the density of topographic masses, which is almost 2.67 gram per centimeter, cube centimeter. It's constant. You can assume this constant, but this is not actually. So simply you can compute this distance between any points there and any points down at the surface. Simply you can do that. And for any point from R to R H prime, R to R plus H prime, we can simply compute this integral in 3-dimensional. It will be 3-dimensional integral to compute the effect of a topographic potential of the topographic masses. That's simple. But if we want to go to spherical harmonics domain, we need to use another way. How? We all know that the inverse of distance between 2 points can be written in terms of the Legendre polynomials. So 0 up to infinity S n Pn cosine of the angle between the points. Let me make sure. I have written this formula in my book actually. I'm looking for that. I'll look at the topographic chapter about topographic masses. Yes, it is. I missed 1 over r here for it. So, and S in this equation will be r over r. Here I have written r prime. Let me write r prime. That's better as I be on the safe side. So it's r prime over r. So if I insert this equation back in here instead of L, then I come to this V. I simply write V double integration from R to H prime rho And instead of then 1 over L, I will write 1 over R summation up to infinity Sn Pn cosine psi d r r prime 2 r prime d r dx. So, and I already know that this S is r prime over r. Now if I simplify this, simply I come to this formula. V will be G integral. This R can go outside because R is, we are not integrating with respect to R, we are integrating with respect to R prime, H prime. Rho, you assume that the density does not change radially. Summation to infinity R prime with the power n and R prime with power 2 will be R prime n plus 2 over R with power n Pn cosine psi dr prime d sigma. So we have R over R with the power n about here, which can go outside the integral as well. This one can go outside the integral as well. And if we rearrange this, we come to this R. I can take it inside this class. Rho T summation from this R will multiply by this one. I will write 1 over R m plus 1. And the integral R m prime R m prime into dr prime Pn cosine psi d sigma. Well, the solution of this integral will be here. So it will be 1 over m plus 3 R prime m plus 3 R plus H prime, which is equal to m plus 3 R plus H prime n plus 3 minus R n plus 3. So we need to work a little bit further on this solution here, the solution of this radial integral, because we cannot directly take the surface integration from this one. Then let me work a little bit on this solution. I will write it in green so you recognize that it's not exactly inside the integral part or the potential. Is some mathematical derivation for simplification of this term. So let me write this equation like that. I continue this here over 1 over m plus 3. I take Rn plus 3 out. I factorize actually, so the result will be 1 plus h over r n plus 3 minus 1. So far, so good, no problem. But we still have problem with this term because n plus 3 is in the power. When it is so, it's very difficult to get the surface, to perform the surface integration. Then I continue this. Instead of this term, I write the Taylor expansion of that. So binomial, so it's 1 plus n plus 3 h over r, or h prime, plus n plus 3 n plus 2 h prime 2 over 2 r2 blah blah minus 1. So we have minus 1 here and we have 1 plus 1, then they cancel each other. We have n plus 3 here and we have n plus 3 here and here, then they will simplify. Therefore, this integral will have this solution. Of course, not the exact solution because I have used approximation. I have used the Taylor expansion up to third term. Then I can say that, okay, it will be Rn plus 3 times h prime r plus h prime 2 2r2 n plus 2, or Rn plus 2 multiplied by h prime plus h prime 2 2r n plus 2. So we solve this radial integral. Now it's time to insert it back to the formula for the potential. If you remember, potential was double integral 1 over n plus 1, and we had a summation here to infinity, and we had the integral, and now the result of the integral is that one. This m and r2 can come here, and here we will have h prime plus n plus 2 over 2r h prime 2 pn cosine. Then we got the potential. So this integral can go inside the summation. Oh, I wrote this wrong because this n cannot be outside the integral. Actually, this should have been here, behind the parentheses. So now I write this potential in another way. So I will write g. This also should be inside. Sorry. And I will write this sigma n from 0 up to infinity integral of, I will write this, I will write them again, Rn plus 2, Rn plus 1, integral h prime Pn cosine psi d sigma plus n plus 2 over 2r integral h prime 2 and I continue here. So you remember the addition theorem? What was the addition theorem? 2n plus 1 Pn cosine is summation over ynm theta of lambda multiply ym prime m prime ynm theta prime lambda. So, and I can write Pn cosine is 1 over 2m plus 1 summation ynm theta of lambda ynm theta prime of lambda prime. So, if I insert this here, I can simplify this integral further. Look. I just solved this part. No. It's double integral. So I solved this part. Integral h prime 1 over 2m plus 1 summation m minus n theta of lambda and m theta prime of lambda prime. This one. So this integral here, this one is here, and this one is here. Therefore, solution of this integral will be 1 over 2m plus 1 summation m minus n to n. Another integral comes in. I think you already have seen this formula. This is spherical harmonic analysis. Analysis of spherical harmonic, this term. Oh my God. This term will be 4 pi spherical harmonic analysis of the heights. Therefore, this integral, the result of this integral, will integral h prime pn cosine, and the potential will be 1 over 2n plus 1 summation, and I have 4 pi here, of course. M is minus n to m, h and m, y and m, theta lambda. So this is the solution of the first integral. And if you remember, we have had another integral which was like that. The integral was, we have had this coefficient behind the integral in the formula, 2r integral plus h prime to pn cosine. Yes. So in a very similar way, if I do this, follow the same procedure, I will come to the following formula. It will be, I write it here, 4 pi 2n plus 1, n plus 2, 2r, if we write both integrals, if you remember the original formula, I will write it again. Potential was G, no, not this one. Or n plus 2 plus 1. Then, then we have had these integrals. Now, these two terms are simplified to this. So if we insert these two formula back instead of the integral one, we come to the following integral solution, the following spherical harmonic solution. So it will be V so 4 pi is constant, can go out. No, I can let me write it as no, it shouldn't. Do not mix it. So it will be, I will write, can I write 4 pi? 4 pi, let me write it. So 4 pi G 1r, I take 1r out, from 0 to infinity, r n plus 1, and the summation comes. I'll keep n plus 1 over n. multiplied by h and m plus n plus 2 over 2r h2 and m y and m theta. Or you may see in some literature that they write the formula for the potential in this form. The potential will be okay, gm over r summation to 0 or r plus 1 v n m is the external. Oh, I missed the summation. V and m epsilon e external or direct y and m theta and lambda. And in this relation, then V and m will be I think I missed this the density somewhere. Density should, oh my god, I missed the density. Rho as well. Can be go inside. It can go inside this potential. So V and M spherical harmonics will be. So 4 pi went inside, and m here is the mass of the Earth. I multiplied a mass and I divided mass. So I multiplied 1r, I divide 1r, then I multiply 1r. So I have divided, so the mass of the Earth, I will come to that later, and the mass of the density of the topography. And we know that the volume of a sphere is 4p r 4p. Yeah. So we have 4p. This if I multiply 1 3 and 1 divide by 3, I have 4p, and the mass of the Earth we have. This will be the density. The density, but density will appear down here, density of the Earth. Therefore, I can simply write that this r is r. This will go away, then I will write 3 2n plus 1 multiplied by h and m plus h n plus 2 2r. Just let me check I have done it correct. It seems so. So that's the spherical harmonics of the expansion of the topographic effect. Or if you do not want to change it to this form, it is very much okay to use this one. If you do not want to consider the mass of the mean mass of the Earth, simply write 4p g r2 divided by 2m plus 1. The same is here. So as you see here, we have a similar mathematical formula to the potential, spherical harmonic of the potential. That's the direct potential, the direct effect on the topographic effect, direct topographic effect. Okay, now we have the topographic effect in terms of spherical harmonics. So, but normally for computing a geoid, you use Stokes formula. Let me write it again. Integral. This is a Stokes formula. Assume that it's modified one. And over the cap size. And we have delta G. But I will write a star. Delta G is downward continued gravity anomaly. Downward continued delta G. So, and if we remove now the gravity, the effect of topographic effect on the gravity data, which means that one, then I will remove the effect of topographic effect, then it should be continued downward. So what does that mean? You have gravity anomalies at the surface. Then you, from the masses and the heights that you got from leveling, you compute the effect of the topographic method on the gravity. The difference between these two should be continued downward to sea level, so you will get delta G star. So, what does that mean? We have discussed about downward continuation. We have had different methods. One was collocation, one was downward continuation using iterative method. One was a gradient method. The other one was solution of the inverse solution of the integral, Poisson integral. This means that you need to continue downward that gravity anomaly, which is reduced for the topographic effect. Oh, this summation should be. Which one is the one which is reduced? Not the gravity directly.